Hello there and welcome to another series, and this will be module 3 of digital electronics and computer organization. The main chapter in this is central processing unit. We will be discussing the CPU in detail, and let's get to it. The CPU is the part of the computer that performs various data processing operations. It is a multi-purpose programmable clock-driven register-based semiconductor device. Basically, it interprets instructions that are given to the computer, and then on that basis it performs the arithmetic logical processing operations, and thus it causes the input and output operations. The major components are the register sets, the ALU, and the control unit. So the CPU has registers. It has the control unit that sends controls to both the registers and the ALU, and the ALU is responsible for carrying out the arithmetic and logical tasks. The register set stores the intermediate data that is used during the execution of the instructions. The ALU is for performing the micro operations while executing the instructions. The calculations include arithmetic calculations, logical computations, shift, rotate, and so on. The control unit, on the other hand, it supervises the transfer of information among registers and instructs the ALU, okay, as to which operation to perform. So it helps the ALU in deciding which operation is supposed to be performed, and also helps in transferring information from one place to another, from the memory to the registers and so on. The transfer component is a common bus system that is used for transferring the data from one place to another and between the components. The general organization of the CPU is as follows. It is made up of the ALU, we have the registers, we have the common bus system, and then we have two multiplexers and a decoder. The registers range from R1 till R7. They are connected to a clock, and the common bus connects them to both the multiplexers. The first multiplexer represents the A bit or the A number, and the second multiplexer represents the B number, so it is the bus for A and the bus for B. The first mux has select lines for A known as SELA, so select A, and the second one has select lines for B, SELB, and each mux also has one input, that is the external inputs. So these select lines help in deciding which resistor is going to be going to A and which one will go to B through the common bus. They both are entered to the ALU, and the ALU then chooses the operation using the OPR selection lines. The OPR selection lines basically refer to the operations, and which operation is supposed to be performed on A and B is chosen through this operation code. And finally we get an output that can either be stored somewhere else, or it can be taken and stored into one of the existing registers. In order to store it into one of the registers, we have the decoder, which is a 3:8 decoder for 8 different combinations, and the SELD, that are the select lines for the decoder, help in deciding in which register we are going to be storing the data. Since we do not have a register named 0, the select lines 000 will be invalid, hence there will be no input at 000. So the multiple general purpose registers are used instead of a single accumulator. The accumulator holds one of the operand and result of the micro operation. Computer uses 2 or 3 address fields in the instruction format, and that stores each address and may specify a general register or a memory word. Use of multiple CPU registers for frequently used variables and intermediate results. We can avoid memory references, so much of the time is saved. Okay, hence it increases the execution speed of the program and also reduces the program size. The output of each register is connected to two multiplexers, which form the two buses for A and B. Select lines in each multiplexer select one register or the input data for the particular bus. Buses A and B form the inputs to the common ALU. The operation selected in the ALU determines the operation that will be performed, whether it's the arithmetic or the logical micro operation. The result of the micro operation is available at the output, which also goes as input to one of the registers. The register that receives the information from the input from the output of the bus is actually selected by the decoder SELD. The decoder activates one of the register's load inputs, hence allowing the transfer path between the data and the output bus, and then it stores the input of the selected destination register. The control unit that operates the CPU bus system directs the information flow. Hence, the control unit is the one that allows the choosing of various components and the operations of the ALU. For example, when we are performing the following operation, which is the summation of R1 and R2 and R3 stored in R1, thus it must provide the selection variables that will allow the execution of such a code. So first of all, we will have mux A selectors that will place the content of R2 in A. Then mux B will place R3 in B. They both will be sent to the ALU, which will have the OPR selector that will provide the arithmetic addition. And finally, the destination is R1. Hence, SELD will be set to R1, thus allowing the load of R1 to enable R1 to get the content of the final ALU addition. The 4 control selection variables are generated in the control unit. So the control unit generates the selections and must be available at the beginning of a clock cycle. So before we start the execution, the control unit must give the selection variables beforehand. The data from the two source registers propagate through the gates in multiplexers and the ALU, and thus to the output bus, finally going to the inputs of the destination register, all during the single clock interval. Now, what is a control word? There are 14 binary selection inputs in the unit. So in the CPU there are 14 selection inputs and their combined value is a control word. So the 14-bit control word is as follows. Since we have select A, B and D, each of them have 3 bits, and the OPR, that is the operation that will be selected in the ALU, has 5 bits, resulting in a total of 14 bits of the control word. 3 fields contain 3 bits each and one field has 5 bits. The 3 bits of select A source select a register for the input A of the ALU, and the 3 bits of select B select for the input B. 3 bits of selection D select the destination register for the output loads, and finally the 5 bits of OPR select the operations for ALU, hence creating the 14-bit control word, which is when applied helps in carrying out a particular micro operation. This is how the select A, B and D are encoded. Since 000 is no register, hence select D is invalid at that point. In select A and B we have the input line, and in rest of the numbers we have the registers that are selected. So if select A has to be R2, then this will be the following encoding, and if select B is R7, then this will be the following encoding, and so on. The 3 binary code listed in the first column specifies the binary code for each of the 3 fields, and the register selected by fields A, B and D is the one whose decimal equivalent is number is equivalent to the binary number. So if we are taking R7 register, then we will be getting the binary equivalent of 111. When SELA or SELB is 000, then we get the external input data. When SELD is 000, there is no destination register, so the components will go to the output bus and are available for external output. The ALU has the following encoding, where the OPR is 5 bits, and these are the following operations that can be performed for each different unique pattern of the bits. So this is an example table that is showing you a specific control word, and on the basis of that control word what operations are performed and which registers are selected. So if the control word is 010, hence that refers to select A being register 2, hence the bus A has register 2, and 011 has register 3 in bus B. Our destination is 001, that means the first register is the destination, and 00101 is the control OPR code for arithmetic subtraction. Hence, we can say that R3 is subtracted from R2 and the result is stored in R1. Similarly, the entire table shows different operations that can be used as examples for the working of the CPU system. Thank you and see you in the next video.